question is often asked of me with a question like this. Is this the one where I use general polar form and have the power as a fraction? Or do I just simply raise the polar form of the complex number to the power of 4? So I'm going to explain this to you today, but to do so I'm going to go right back to the start of the question. So to start a question like this, you're going to be asked, you're going to be given a complex number in rectangular form. So z is equal to minus 8 plus 8 root 3i, and asked to find that in polar form. So in polar form, you're going to need to find the modulus and the argument. So rectangular form is something we're familiar with, and I hope that everyone would be able to plot the point minus 8 plus 8 root 3i on your Argand diagram. With that, it's the same as coordinate geometry. You're going left and right and up and down. So minus 8 plus 8 root 3, you're going 8 units to the left of the origin, and then you're going 8 root 3 units upwards from the origin, and that brings you to your point. So I hope we'd all be familiar with that. However, when we're talking about polar form, you're identifying the location of the point using the distance from the origin and the degree of rotation anti-clockwise from 0 degrees. So it could be 2, 120. It could be something like that. I think in this case it'll be 16, 120. And 16 would be the distance from the origin, how far it is from the origin, and the 120 would be the degree of rotation anti-clockwise from 0. So going between rectangular form and polar form is the equivalent of going between degrees Celsius and degrees Fahrenheit. It's just two different ways of measuring the same thing, and whichever one you're more used to is the one you find easier. We're more used to rectangular form, so that's the one that we're most comfortable with. Okay, let's get this into polar form. The first thing we're going to do is try and find our argument, theta, the degree of rotation anti-clockwise from 0 degrees. We can't find that straight away because it's an obtuse angle, so we're going to use our reference angle alpha within the right angle triangle formed by dropping the vertical from minus 8 plus 8 root 3i. So we're going to use tan because we have this right angle triangle, we have the opposite and we have the adjacent. Some people will point out that that should be a minus 8 units because it's 8 units to the left of the origin, and that is correct. However, when we're getting alpha is just an acute angle, so it's the positive version of the adjacent we're going to use, because we're just finding the magnitude of the angle. So we say tan of alpha is equal to the opposite over the adjacent. So you can see the 8 will divide into 8. You're just going to have tan alpha is equal to root 3. So you're going to have alpha is equal to the inverse tan of root 3. So the inverse tan of root 3 is going to be, if you have your calculator in radian mode, you're going to be on pi over 3. And pi over 3 is going to be 60 degrees. Okay, so inside here, I'll just write it as in degrees, 60 degrees. And of course then, if we want to find alpha, well, we know it's pi radians is one, straight line. That's the same as 180 degrees. So if the angle is 60 for the reference, it'd be 120 for theta. If it's pi over 3 for the reference, it'll be 2 pi over 3 for theta. Okay, so we've shown that the argument of z is 2 pi over 3. The modulus, or you can use Pythagoras' theorem, r squared is equal to 8 root 3 squared plus 8 squared, or some people will think about it as r is equal to the square root of the real part squared plus the imaginary part squared. And again, I'm dealing with, I'm calling that plus 8 there, you know, when I'm squaring it. But you can use minus 8 as well. And I'm going to get square root of 256. I'm going to get 16. So I have my modulus is 16. So in its simplest form, you could call this, in polar form, you could call this 16 comma 120. Okay, a distance of 16 and a rotation of 160, or 120 I should say. Or you can say, well, in polar form, minus 8 plus 8 root 3i is equal to, and this is the way we write it in complex numbers, we say it's r, which is 16, times the cos of the argument, cos of 2 pi over 3, plus I sine of the argument, 2 pi over 3. And in degrees, that would be 16 times cos 120 plus I sine 120. Okay, so there we go. That's our connection between rectangular form and polar form. Now, this says here, it says use De Moivre's theorem and find z to the power of 3, giving your answer in its simplest form. Okay, so we'll do it first in radian measure. So in using polar form, I can say z is equal to 16 times cos 2 pi over 3 plus I sine 2 pi over 3. We know that on page 20 of the table books, we have De Moivre's theorem. Not written in general polar form, just you note that, but just in its simplest form, where it says r, which is your modulus, times the cos of the argument plus I sine of the argument to the power of n is equal to r to the power of n times cos n theta plus I sine n theta. So you can see here the modulus gets raised to the power and the argument gets multiplied by the power. I'll explain that one again in a moment. But we're going to use De Moivre's theorem in that sense here. Now here's again where the students will be saying, but how do you know it's not the general polar form? Well, okay. There's a couple of clues in there. It's saying find z to the power of 3. So we're given z and we're just asked to find z to the power of 3. So that sounds like it's, you know, relatively kind of straightforward. You're just cubing it. And it says to this, give your answer singular in its simplest form. So all of those are indicating to me that I'm just using De Moivre's theorem in its straightforward version. So we'll see the other version in a moment. So in this case, I want z to the power of 3. So I'm raising the right hand side to the power of 3. So the whole thing is to the power of 3. I now apply De Moivre's theorem. The argument gets raised, the modulus gets raised to the power of 3, and the argument gets multiplied by 3. Okay, so it's 16 times cos 2 pi over 3 multiplied by 3 plus I sine 2 pi over 3 multiplied by 3. And to be no problem, have it, the 3 could be written in there just the same. You know, you're multiplying the angle by the power. So you're going to get 4096 times cos 2 pi plus I sine 2 pi. Now you can use your unit circle here, or you can put it into the calculator in radian mode. And either way, you're going to get 1 for cos 2 pi. You're going to get 0 for sine 2 pi. So you can get your answer in the form of x plus yi. It doesn't actually say it there, but that's the form you'd give it in. 4096 plus 0i. So let me just show you that in degrees. So if z was equal to 16 times cos 120 plus I sine of 120, I could say z to the power of 3 is 16 cos 120 plus I sine 120 to the power of 3. Now this would be, the whole thing would be to the power of 3. There'd be a square bracket there. I'm going to use De Moivre's theorem. So again, the modulus gets raised to the power and the argument gets multiplied by the power. So you could have the 3 before the 120 as well. It ends up as the same thing, 4096 times cos 360 plus I sine 360. Cos 360 is 1, sine 360 is 0. I get 4096 plus 0i. Okay, that's my answer for that part. Now we move on to the last part, where it says find the values of w. such that w to the power of 4 is equal to z, and give your answer in the form of a plus ib. Now, the clue here that I'm going to use general polar form is the fact that it says values. Find the values of w, and then when it has something along these lines, w to the power of 4 is equal to z. When it says something like that again, what we're doing is we're solving for w. Now, by right, it should say answers in the form of a plus ib. Okay, but here we're talking plural, the values of w, and we have this clue in here. Now, I'm going to write this firstly out in degrees, and then we can do it in radians. So we know that we had minus 8 plus 8 root 3i was equal to 16 times the cos of 120 plus I sine of 120. Okay, now that's what z was equal to, and we know that w to the power of 4 is equal to z. Now I'm going to go into what they call general polar form, and I can say so that w to the power of 4 is equal to 16 times the cos of 120 plus 360n plus I sine of 120 plus 360n. And you know from my examples in trigonometry that the 360n is coming from if you're going around the circle another time, you're traveling another 360 degrees, you land back at the same point. You can go 720 degrees, 1080 degrees, 360 degrees multiplied by any number, any whole number, and you land back at the exact same point on the circle. So the general polar form just involves adding in the 360n when you're dealing in degrees. We need to solve for w. How do you solve any equation? You get the variable on its own. So we want to get w on its own, so we're going to have to raise the left hand side to the power of a quarter. We're going to do the same for the right hand side. So what's going to happen here? I'm going to apply De Moivre's theorem. So I'm going to write this part out in red here, but I'm going to leave a little gap for the applying of De Moivre's theorem. You'll see what it is now in a moment. So it's similar to what we just had, but I'm going to apply De Moivre's theorem, and as we know, the modulus gets raised to the power, so in this case it's the power of a quarter, and the argument gets multiplied by a quarter. Okay, so we know then that 16 to the power of a quarter is going to be 2. I'm going to get 2 times the cos of 30 plus 90n plus I sine of 30 plus 90n. What's going to happen next is I'm going to take my different values for n. I'm going to let n equal 0. I'm going to get 2 times the cos of 30 plus 90 times 0. So that's going to be cos 30 plus I sine of 30 plus 90 times 0. So that's going to be the sine of 30. So I'm reaching over here to get my calculator. Well, we know in degrees that the cos of 30 is going to be equal to the root 3 over 2, right? And the sine of 30 is going to be half. But you'd always take your time with it and make sure. So you're going to get 2 times root 3 over 2 plus I sine of 30, so a half times I, and you're going to multiply through there. You're going to get yourself root 3 plus I. Now that's your first answer. Okay, that's your first answer when n equals 0. Now I might need to clear a bit of space here for me in a moment, but I go over here to the left hand side. Let's see what we can do. We'll say when n is equal to 1. So I'm back here at this point here, right? I'm putting in n equals 1. I'm going to get 2 times the cos of 30 plus 90 times 1. So cos of 120 plus I sine of 120 Okay, so we're going to be in the second quadrant there, where cos will be negative and the cos of 120 is going to be minus a half. So I'm going to get 2 times minus a half, and this is going to be plus root 3 over 2i. So that's going to be equal to minus 1 plus root 3i. So that's my second answer. This is my first answer. I can then say let n equals 2. So n equals 2. I'm going to get 2 times the cos of 30 plus 90 times 2. So that'll be 90 times 2 is 180 plus 30 is 210 plus I sine of 210. So the cos of 210, again, you're down where cos is negative. So this is going to be minus root 3 over 2. So I'm going to still have my 2 times minus root 3 over 2. Sine is also going to be negative in the third quadrant. So I'm going to get minus a half I. So what am I going to get? I'm going to get minus root 3 minus 1 I. And then my last one, I'll have to just steal a bit of space down here. Okay, so I'm going to say, well, n equals 3. When n equals 3, I'm going to get 2 times the cos. Well, what will I have? 3 times 90 is 270, plus the 30 is 300, plus I sine of 300. So in this case, you're back where cos is positive. You're going to have a half plus the sine is going to be negative, so it's going to be minus actually. Sine will be negative in that fourth quadrant. We're at 300 degrees. So I'm going to have minus root 3 over 2 I. So my point then will be 1 minus root 3 I. So I have my four answers. And of course, they're all quite similar looking to each other. Those are my four answers. I'm going to do one thing here, right? I'm going to skip through one little part and show you the final answer as a diagram, and then come back to the radian measure part. So if I plot my 4 points when n was 0, when n is 1, when n is 2, and when n is 3, you could see your 4 points are all plotted on the Argand diagram. They're all 90-degree rotations from each other. The distance from the origin would be the same in each case. So they form that circle. If you put in, by the way, if you put in 4 for n, you get back to root 3 plus I, you get back to where you are at the very start. Okay, you get back to where you were at the very start. Okay, let me just do that in radian mode very quickly for you. And in this case, you could do it in either, right? Because of the fact that, you're just looking for your answers at the end. So in this case, we can say, okay, w to the power of 4 is 16 cos 2 pi over 3 plus I sine 2 pi over 3 in radian form. So we're going to be using the general polar form here. But of course, 360 degrees is the same as 2n pi. So in this moment in time, I prefer to think about it like this, just with the everything here. So like this is, this was w, right? Remember when we were back up here at the start, we had w to the power of 4. But what happened, let me just go back here for 1 second. When we had w to the power of 4, like basically you're raising both sides to the power of a quarter. So you're raising both sides to the power of a quarter. So in this case here, when we're in general polar form, we've added on the 2n pi. And the reason we've added on the 2n pi is because, well, 2 pi is the same as 360 degrees full rotation. And similarly with degrees, you can multiply that by n. It doesn't matter, just as long as n is a whole number. I'm going to use De Moivre's theorem. The argument, which was the 16, gets raised to the power. 16 to the power of a quarter is the 2. Okay. What's happening here with the other part is I'm multiplying the argument. So the modulus got raised to the power and the argument is getting multiplied by the power. So when you multiply 1 quarter times 2 pi over 3 plus 2n pi, you're going to get you're going to get 2 pi over 12 plus 2n pi over 4 when you multiply the quarter through that bracket. Firstly, I've simplified that down to 2 pi over 12 plus n pi over 2. 2 into 2 goes once, 2 into 2 goes twice. But I can also simplify down the 2 pi over 12 to pi over 6. So I get down as far as here, 2 times cos pi over 6 plus n pi over 2 plus I sine pi over 6 plus n pi over 2. And again, what do? I start off, I put in 0 for n, and I get 2 times cos pi over 6 plus I sine pi over 6. Remember, the pi over 6 is 30 degrees. When I put in, I can type that into the calculator, or I can use my unit circle, and I'm going to get my answer of root 3 plus I. That's my first answer. For n equals 1, I'm going to have 2 pi over 3. 2 pi over 3. Remember, I'm putting in the 1 up here. So I'm getting, pi over 6 plus pi over 2. That's the same as 2 pi over 3. I'm typing cos 2 pi over 3 into the calculator. I'm getting minus a half. I'm typing sine 2 pi over 3 into the calculator. I'm getting root 3 over 2. I end up with minus 1 plus I times root 3. I do the same here then for n equals 2. So if you're putting in n equals 2 here and here, you're going to get the 2's will cancel into each other. So you're going to get pi over 6 plus pi, that's 7 pi over 6. That gives you, when you type it into calculator, cos of 7 pi over 6 is minus root 3 over 2. Sine of 7 pi over 6 is a half. So you're going to end up with minus root 3 minus I. And for n equals 3, you get 2 times cos 10 pi over 6 plus I sine 10 pi over 6. So when you're putting in the 3 for n here, you're going to get 3 pi over 2, add that to pi over 6, you get 10 pi over 6. So cos of 10 pi over 6 is a half, sine of 10 pi over 6 is root 3 over 2. You multiply through, you get 1 minus I times root 3. You put it, this is your kind of, your complex number in general polar form. As I said, we have our 4 answers. And again, if you put in 4 for n, you get right back to where you started. The first one. If you put in 5 for n, you get your second one, etc., etc. So I hope that's clarified it for everybody. Where you use the general polar form, generally you're going to have something like this written down: w to the power of 4 is equal to z. You're solving for w. There's going to be a clue in there somewhere that you need more than one answer. That's when you use the general polar form.